Time to start the talk by Konstantin on quantum K-theory, Calabi-Yau, and Ginsburg correspondence. Like any good correspondences, it's a correspondence within four people. When two pair here, one pair of people corresponds to another pair of people, and so please, Konstantin,
Yeah,
take
exactly.
it away.
Thank you. Thank you for having me here. It's really nice to give a talk at this seminar again. So, in different subject, it's kind of a theme that I'm giving talks on the seminar on the stuff I haven't finished. But so this is work in progress. With Melissa. So yeah, I want to organize my talk as follows. So first, I want to talk a bit about. I mean, basically, I'm going to talk to devote most part of my talk to some known subject. That is, yeah, basically the classical correspondence between these four people, and yeah, and then I was just going to explain what we're doing right now in trying to lift this Calabi-Yau and Ginsburg correspondence to the K-theory. And yeah, so let me start. Yeah, and actually yeah, okay, let's start with the quintic threefold, which is something I really like. I can call this Z, so it's zero locus of a fifth order polynomial. And well, there are enumerative theories associated. We can associate to this quintic, and the theories I will be interested in today is basically quasi-maps. Quasi-map counts associated to Z. Well, and now there are again there are ways to relate this quasi-map count, let's say with stable maps counts or with Donaldson-Thomas counts, but yeah, but I will be interested in quasi-map counts. And also there are ways to associate different quasi-map counts to, let's say, to the usual quintic. And yeah, let me describe them briefly. So another way to represent a quintic is the following. So we can write it as a subset of the total space of the line bundle of -5 over P4, which is a critical locus of some polynomial W on this total space. So I'll call this space Y. So W is polynomial from Y to C, and explicitly Y is given by, sorry, W is given by, let's say, P times some 1 to 5 xi power 5, where these are homogeneous coordinates on P4. On P4. And this is just a coordinate in the fiber of this bundle. So coordinate in the fiber of -5. So this of -5 is taken so that this whole expression is an invariant function and has a critical locus on this total line, sorry, on this the total space of this line bundle is exactly the quintic. So it's like p equal to 0, and maybe I'll write it like embedded into P4, which is a 0 section of this line bundle. All right, and so there is a theory associated to this, some Landau-Ginzburg type theory associated to this construction. So let me draw some diagram. Consider quasi-map counts. So one theory is Z itself, that is our quintic threefold. Another theory is quasi-maps into this total space of this line bundle Y. And another theory is what's called gauge linear sigma model into so gauge linear sigma model into this total space of this line bundle with a superpotential W. Later I'll briefly recall what does it mean, how to count such quasi-maps. And well, there are correspondences between these quasi-map count theories. So, and the correspondence between quasi-maps into Y and Z is called quantum seriality. Has been worked out, I think, by Konstantin and his students and some other people. And the correspondence over here is very closely related with what Renato's thesis was about. So it's done by comparison of virtual fundamental classes associated to corresponding counting theories. Comparison. Yeah, I don't know if there is a good name for this correspondence of virtual fundamental classes. And so far there is no Landau-Ginzburg-Calabi-Yau correspondence, but so I left some space on the right of this diagram, so there's going to be some. And in order to describe this, I will actually use the fact that this Y, I mean, all of these constructions are basically very well behaved from the point of view of toric geometry. So we can think of Y as the JT quotient of C6 with respect to C star, so which acts with weights 1, 1, 1, 1, 1, minus 5 on the C6. And if we take the quotient, removing the common 0 locus of first 5 coordinates on C6, then the resulting quotient will be exactly the total space of minus 5 over P4 in this case. And well, one might ask what happens if we change the stability condition, if we go to another stability chamber. And well, so the answer is not very complicated. So if we take JT quotient with, there are only 2 stability chambers for this JT quotient. So this X is just C5 modular diagonal action of group of roots, 5th order roots of unity. So this is diagonal action. And this is a static quotient. And the other related theories are come from this other stability condition associated to this story. So we can just consider quasi-map counts to the stack X. That is this just C5 modulo mu5. And we can consider some GLSM counts or FGRW counts into X with superpotential small w, where superpotential small w is just a sum over xi power 5, where xi are coordinates on this C5. So this big W is like small w times p from the point of view of graphics. From the point of view of mathematics, one has to be slightly more careful. All right. So let me complete this diagram. So these two guys are related with something that is called multiple log canonical correspondence, which is basically which is for me some version of quantum seriality. Okay, correspondence. So I'm writing it with the same color. Correspondence. And well, so the remaining part is how we relate the left-hand side with the right-hand side. And so the relation of quasi-map counts into these two different JT quotients without potential, without superpotential, go under the name of Krepan transformation conjecture. And the correspondence between these two, so these two guys are very closely related. So I will not distinguish between them too much until later. So this relation is called Calabi-Yau-Landau-Ginzburg correspondence. So this is called FGRW theory. So, and the thing I will be interested in is exactly this last line, which is arguably not the simplest one among all of these relations, but somehow I started doing all of this from the bottom. So this is the topic I know most about. All right. So yeah, maybe actually I should write some names. So maybe I'll write them below because this diagram is already slightly over used. Yes, let me comment a bit on Krepan transformation conjecture. Well, in the case of the quintic, we have a singular manifold C5 modulo mu5, and then there are two Krepan resolutions. So one Krepan resolution is the stacky resolution. So this is a singular variety, but this is a smooth Delimovre stack. And another Krepan resolution is Krepan is exactly this Y. So total space of 5. It's a blow up. It's a blow up at the origin of this singular variety. So Y is blow up at the origin. Toric blow up, actually. And yeah, and Krepan transformation conjecture states that, well, independently of how, like, of which Krepan resolution we take, the resulting theories are going to be similar. But this is not something I know much about. And yeah, maybe I should write some paper, some names. One of the papers is by Coates. Tom Coates, Ritani, and John. So e.g. Yeah, I mean there are lots of people involved into all of this, and probably I mean surely I'll miss many names, but this is already some. Right. So Landau-Ginzburg-Calabi correspondence is something that originally was done earlier. So it's called Calabi-Landau-Ginzburg correspondence because on the left-hand side we have an enumerative theory of maps into a Calabi variety, and on the other side we have FGRW theory, which is sometimes called a model Landau-Ginzburg theory in mathematics literature. So this is why we have these names. And yeah, there are a few papers like Kyoda, Iritani, Ruan from, I think it was published at 2014, but it was on archive in 2012 or something like this. Yeah, then maybe there is another paper by. So this was done. This is for Fermat hypersurfaces. Lipridis, Shellmaker from 16. So I believe this was done for more than one modeling, say for the quintic threefold. Yeah, and then many more. All right. So now I want to talk more about the thing I'm interested in, about this Calabi-Ginzburg correspondence. So, and well, the input that we take, well, there are different ways we can compare enumerative theories, and the input we will take is going to be basically I functions. So those are some generating series of enumerative invariants. And so the old way of thinking about I functions, which I had, was like old-fashioned mirror symmetry picture, where components of I functions are period integrals of a mirror manifold. But already for a while, there is another perspective on I functions, that those are actually generating series of actual counts, but of quasi maps instead of stable maps. And in all of these 5 cases, we can actually let me call them some numbers. So it's 1, 2, 3, 4, and 5. In all these 5 cases, we can compute these I functions using torus localization and graph spaces. Well, millisecond, to be more precise. And these I functions, in order to describe these I functions, we need to start with what's called a state space. Associated to the theories, maybe to quasi-map counts. I think I'll just describe the state spaces of theories I'm most interested in this story, 3, 4, and 5. And if time remains, then I'll also describe the remaining 1 and 2, which are arguably simpler, but they still require some different exposition. So for just quasi-map counts into the quintic, we just need to consider. So I'll write H for the state space, the quintic, and it's just the ambient part of the cohomology of the quintic. And what's an ambient part is an image of I star, where I is an embedding of the quintic into P4. So this is just the even part of the cohomology of the quintic. This is just generated by the hyperplane section modulo P⁴. And there is a pairing on the state space. Of course, there is a Poincare pairing, but we're interested in K-theory pairing. So it takes two elements, cohomology element 7b, and send them into A times B times the Todd class of the quintic. So if one thinks about A and alpha and beta as Chern characters of some line bundles, then this pairing is exactly the Euler characteristic pairing from K-theory. So 4, and I already told that 3 and 4, that is quasi-map counts into the quintic and into the total space of line bundle with superpotential are very similar. And so the state spaces are isomorphic. But actually the state space is some relative cohomology of the ambient part of Y relative to real part of W greater than 0. So this is this relative cohomology. Yeah, so maybe one remark. So in the talk I'll work over C, because so I'll switch between cohomology and K-theory, and over Z there are some non-trivial torsions, but over complex numbers these things become much easier, and also yeah. So and this is basically, so one can think about this as differential forms on Y modulo twisted de Rham differential. And well, by the usual argument, for example, this like this old story where one can use some supersymmetric field theories to prove Moore theory, theorems from the Moore theory. One can argue that so this should be equal to the cohomology of the critical locus of W on Y. And critical locus of W is just Z. So yeah, and all the pairings are, particularly the pairing that we're going to use is preserved by this isomorphism. So basically we don't need to distinguish between 3 and 4 too much. And what about the state space for 5? Oh, sorry, it's not Z, it's actually Y. Okay, sorry, sometimes cannot switch colors for my notebook, and then I have to do some strange things to get it to work. All right. Yeah, so what about state space for the FGRW theory? And this is just the orbifold cohomology or Cherenkov cohomology of x relative to real part of w much greater than 0. And x, I remind that is just C5 modulo mu5. And it turns out that, well, so what are orbifold cohomology? Those are just cohomology of the inertial stack. So we have stack X and inertia stack. In the case where we have some abelian quotients, inertia stack is very simple. So it's just a disjoint union of, maybe I'll write it like this. So it's a disjoint union of the stack itself and a copy of invariant locus of group elements of this mu5 associated to each of the group element. So in this case, it's just point modulo mu5 or b mu5. And it turns out that the state space is just generated by cohomology of state space, sorry, is generated by cohomology of twisted sectors. So these guys are called twisted sectors. Those are associated with non-trivial group elements of mu5, and this is untwisted sector. Oh, sorry. So this is just sum I goes from 1 to 4, C times generator of the corresponding component, which I'll call 1 with index maybe k. I looks very weird sometimes. K over 5. So yeah, and from the first glance, we can just look at dimensions of this as vector spaces, and well, this is as a vector space is it's just C4, and so is this state space. So there is some good sign that this correspondence is not completely ridiculous. Yeah, and then let me describe the corresponding I functions. Associated to the quasi-map counts. So yeah, maybe if some time remains, I'll try to describe to the best of my knowledge how to construct these I functions from the derivative counts. But you could think about them as some input to the theory. And let's start with, so I functions are state space valued functions of or the Keller variable, which I'll describe later. And equivariant variable. And yeah, and unfortunately there are many annotations, and most of the annotations contradict each other, but I'll try to follow, to take one notation that will be at least consistent throughout my talk. Yeah, and let me write some I function that is associated to the quintic threefold itself. So this I function has been known since like early 19th, in fact. I mean, even before it got the name I function. So I'll explain notations after I write the formula. Okay, sorry. I'm actually trying to write it more general, but now I'll just do it for the quintic. All right. Actually, I don't need to use 2 lines for that. Q power D. So, what is written here? So this Q is a Keller variable. Keller variable. It counts the degree of the quasi-map. Counts the degree. So maybe you can think about term in front of Q power D as a number associated to quasi-maps of degree D. And while P is a hyperplane class on Z, so it's element of the state space, this guy. So Z is a covariant variable associated to the target P1. So one can think about quasi-map as like some map from, yeah, it's all this, the whole story is about Geno 0. So it's about maps of P1, maybe with some mark points into something, and in this case into the quintic. And Z is the variable. Okay, I think I have to do this again. Sorry. Sometimes I have to restart my notebook, but it looks like I can do it without this. So yeah, so this is some cohomology valid function, and how do you think about special functions of Keller variables, which are, well, not exactly numbers. If you haven't seen it, probably you have seen it, but you can just Taylor expand all these things. And also this ratio of gamma functions is in fact just a product of, so it's basically a rational function of P and Z. So I wrote it in this form for later convenience. So yeah, and maybe I'll write the I function associated to the 4 as well. So it's basically if we plug in -1 power D, then it becomes I function. And also we have to Yeah, okay, let me write that. So I, y, comma, w. So I already told you that state space of these two enumerative series, 3 and 4, are isomorphic. And the I functions are almost the same. So they differ by some sign in each summand. And what about the I function of the FGRW theory? So let me also write it down. All right. So this angular brackets is a fractional part of x. And this 1 sub something over 5 is an element of the state space. So a state space is generated by 1 sub 1 over 5, 2 over 5, 3 over 5, and 4 over 5. And if d is integral, then actually, yeah, minus 5z. So if d is 5 times integer, then this gamma function in the denominator has a pole. So this whole expression vanishes actually. So those are some special functions associated to these 3 theories. And the point is that these functions satisfy same differential equation in the Kähler variable q. And in fact, one function can be obtained as analytic continuation of another. And this is what I'm going to describe right now. So do this. The relation. So the Landau-Ginzburg-Calabi-Yau correspondence between 3, 4, and 5 can be achieved by the analytic continuation of by Mellon-Barnes analytic continuation of the I functions. And in physics literature, this was known in 2013. So Hori and Roma 13 in physics. And what is nice that the integral that, the analytic continuation is done using the integral that has direct physical meaning. It is called the disk partition function. So I'll call it z sub d2 of b, and b is a brane. I'll I'll say a couple of words about it later. So it's a very simple looking integral for our quintic. So yeah, it's a contour integral where the integrate is product of gamma functions. Then there is exponential containing our Keller variable q, and there is some factor f b sigma, so it's called brain factor. And it has a form, it has a trigonometric form, so it's sum over t and z ct exponential of 2 pi I t sigma, where only finite number of CTs are non-zero. So one can think about this as some equivariant Chern character. Of some representation of our group C star, and C is one can identify this variable sigma with an element in the Lie algebra of C star. So the algebra of C star from the GIT quotient. All right, and so what does this have to do with our previous story with all these I functions? Is the following fact. So depending on the sign of q, sorry, of logarithm of q, one can evaluate this integral by residues either using the poles of this function gamma of sigma or the poles of gamma of 1 minus 5 sigma. So let me write this in. Sorry, give me a second. So if log q is smaller than 0, so one have to actually to satisfy some bounds, so this whole thing is convergent. So if b is such, okay, so if sorry, let me actually write it in slightly different way. So let all of these guys satisfy some condition, which I'll return to later. So 2 pi it plus imaginary part of logarithm of q it actually has to be in between 5 pi, there is no pi here, and minus 5 pi. Then ZB D2 converges. And moreover, if logarithm of q is smaller than 0, then this is equal to some expression involving I function of the total space of O of -5 over P4 with the superpotential. So it is equal to the pairing of I function of y comma w times inverse gamma class y times w, which I'll explain later. Itty tiny gamma class. And character of B plus. So this is a pairing on the state space that which we discussed above. And what is B plus? B plus is an element of K theory. So K theory, enumerative K theory of matrix factorizations YW. That is associated to this expression B over here. Associated to B. So I function is the one I have written, and then this also I have to write that Z is equal to. So there is a covariant variable Z, and then we have to set it to some fixed value, and it turns out to be minus 2 pi root of minus 1. And this expression actually goes under the name of H function in the literature. So it is this Y. It is better. So it is another some linear combination of let me put it like this. So I function is a solution to some differential equation, Picard-Fourier differential equation, and then H function is just gives another base of solutions of the same differential equation. So it's explicitly it is so gamma class consists basically consists of these gamma functions, and effectively it kills some of these gamma functions in the expression. So what we get is, yeah, after my notebook unfreezes. So it is a simpler version of an I function from the point of view of the story. It is transcendental expression though, because as I mentioned, I functions, each coefficient in front of I function is some rational function of these arguments. But when we go to H functions that are I functions multiplied by gamma classes, the coefficients become transcendental expressions involving. So if we Taylor expand them, then we'll get some zeta functions and some other like Taylor coefficients of gamma functions. All right. And So this was the second part of the proposition, and the third part is if log q is greater than 0, then this disposition function gives us a similar expression involving I functions of the FGRW, so on the Ginzburg side of the story. What was that? So it's x small w times so the corresponding gamma inverse of the gamma class paired again with Chern class of B minus. So this guy is in enumerative K-theory of matrix factorizations of x with superpotential small w, and this is pairing on the corresponding state space. And again, this is a simpler version of an I function. So this is all right. So like in a couple of words, this is one way one can think about the classical, which is sometimes called cohomological Calabi-Yalom-Ginzburg correspondence. So the I functions containing enumerative invariants of the theories on the left and right hand side can be related by analytic continuation of this form, and so maybe I should make a remark that this K theory on the Calabi-Yau side, so K theory of matrix factorizations of Y with big W, is actually isomorphic to K theory of just Z, so K theory of coherent sheaves on the quintic, and analytic continuation of I functions is compatible with Arlov equivalence of the categories on the Calabi-Yalom-Ginzburg side. So actually, it is like Arlov equivalence is a lift of this correspondence from K theory to actual derived categories. So dB, I guess, of Z. And derived category of matrix factorizations on X and small w. Yeah, there is some interesting story happening here. Maybe I note about it. I talk about this very briefly. So this integral over here converges only for certain brain factors. So yeah, maybe I should tell you what B is. So B is so I told you what FB is, but I didn't tell you what B is. So B is in K-theory of matrix factorizations, equivariant matrix factorizations. In this case, it's C star equivariant of C6 with the superpotential W. And from the point of view of K-theory, such matrix factorization is a sum of C star representations. So I mean, it's just C star representation that decomposes into C star characters. And this brane factor over here is just sum of these characters. So when we think about exponential 2 pi I t sigma as the Chern character associated to the line bundle of weight t. And depending on imaginary part of Q, so here Q is actually some analytic variable, not just a formal variable. Depending on imaginary part of Q, if I want the integral to converge, then we'll have to pick, pick representations, C star representations, entry matrix factorization only from a certain range. And so changing Q, varying Q, we can actually get different analytic continuations for our I functions. And those are, and this is exactly what happens in our law of equivalence, because basically there is like, for our law of equivalence between these derived categories, there is actually, then there is not just one equivalence, but there is an infinite series that corresponds to infinite number of windows for imaginary part of logarithm of Q. All right. So now I actually want to turn to the K theory, so to the subject. So everything I wrote above is known. So there are not too many new things here. Like one of this, and and actually I've been doing like or rather we've been doing with Melissa a few things related with such Landau-Ginzburg-Calabi correspondence, because you could also wonder what happens if we have more general GIT quotients. And so another work in progress is about the mirror quintic, where you have lots of stability chambers, and then we're studying how I functions in different chambers are related to each other. Yeah, but today I'm going to talk about another direction, that is, we're considering the same quintic, or maybe slight generalizations. But now we want to talk about K theory. So here, if you think about I functions, I function is some object that is usually associated with quantum cohomology. So its coefficients of the K theory are, elements, so some integrals on the moduli space of quasi-maps. And so K-theoretic analog arises when we think about Euler characteristic of some sheaves on the same moduli spaces of quasi-maps. And I functions, corresponding I functions have been worked out in most cases. So what happens now? Now we have to modify our state spaces for theories, because before there were some cohomology theories of like quintic of some relative cohomology, and now we are talking about K theory. So for 3, the state space, I call it HKZ, is equal to a numerative K theory of the quintic. That is C S plus minus over 1 minus s power 4, where s is class of 1. And the pairing on the state space is just the Euler characteristic pairing. So for quasi-maps into total space of minus 5 with superpotential, the state space is actually K-theory of matrix corresponding matrix factorizations. But it turns out it is isomorphic as a vector space, the K-theory of Z. And for 5, it becomes more interesting because, so first of all, I'll write H twiddle of K of C. So this is just C5 modulo Mi 5. So this is just the K-theory of matrix factorizations of X with small w. And this is, well, this turns out to be sorry, let me actually say something about this later. But this is a wrong state space to consider, as we learned. It is wrong from, like, both from the enumerative geometry side and from the side of analytic continuation. So originally, it turns out that I did some analytic continuation of some integrals. And then the result kind of surprised me because I didn't know much enumerative geometry at the time. So this is the state space, for example, I expected. But at the end, I got more elements, more solutions. So, and on enumerative side, geometry side, this is a problem of what is called fake and true quantum K theory according to Giventhal. So this corresponds to the fake. Quantum K theorem. So which I don't want to just to go too deep into. And the state space that turns out to be correct for our story is actually K theory of matrix factorizations of the inertia stack of X. So this is inertial. Yeah, I'm not sure about how theory. So this is actually bigger than the original thing. So this is a direct sum of the naive state space. So of K theory of matrix factorization of X plus components corresponding to twisted sector. So I recall that inertial stack of X is just X, which we call it, say, X naught. And then there are 4 twisted sectors that are just point modulo mu5 in our case. And in this case, well, what is the superpotential on the point modulo mu5? It vanishes, so the matrix factorizations are trivial, and therefore there are also components of K theory of these twisted sectors. All right. So yeah, the thing is that this is still isomorphic to C4 as a vector space. But this thing is much bigger. So this is isomorphic to C4. As we know, because there is a Chern character from this K theory to the state space, like to cohomological state space. And yeah, all of this like Chern characters and the state spaces have been worked out by many people. And yeah, in particular, we used some old story by Borisov and Horja to make this rigorous. But I guess maybe there are other ways to do this correctly. Right, and so this thing is isomorphic to C24. That is 25 minus 1. Or rather 4 plus 20. Well, sorry. Stuck in elementary arithmetic.
So does it mean that the corresponding whatever differential or difference equation would be of order 24?
Exactly. So the difference equation turns out to be of higher order than the differential equation. There are more solutions. Yeah. And this also has been known. I don't know how long exactly, but we learned about one paper which was out in November of the last year. Yeah, where someone wrote the difference equation of in parallel to what we have been doing. So this is some interesting phenomenon.
But this is you doing for like for actual virtual fundamental class, not any. Oh, okay.
Yes, exactly. So this is like what is this fake and true? Yeah, this corresponds to true quantum K theory according to Giventhal. So true quantum K theory.
Well, let it be an open question. What is the true quantum K theory?
Yeah. Well, so I put this parenthesis for this reason. Yeah, but the point of that, like, so one way to define this Riemann-Roch formula, and the usual Hertzsprung-Riemann-Roch formula gives this like this fake quantum K theory, and the Kawasaki Riemann-Roch formula, that is an orbifold version, gives this true quantum K theory. So that's kind of the difference from the point of view of enumerative invariance. Yeah, the wording is so it's a quote. It's not how I don't what the word for this. Yeah. Anyway, so let's leave it at this.
Do these modular spaces have a other spin, or do they have a? So, but you know, what we like usually. No, what we usually like to do is not to take the virtual structure shift, but instead track the virtual roof chains.
Yeah, that's right.
Are these guys spin? I mean, does it even exist for these modular spaces?
Yeah, these modular spaces are like, because we're working with Quasimap, this modular space is actually very simple. So yeah, if I'm not mistaken, then the modular space. So yeah, take with a grain of salt, but example of modular space for this XW is something like Quasimap. It sounds like this P5, 5, and there are like 5D plus 1 copies where there is some degree count. So it's just like P, some projective space modular with a trivial action of Z5, of mu5. And then there is some abstraction shift.
Oh, okay, so it's virtual canonical is something very simple, but
Exactly.
I wouldn't be able to compute in real time whether it's even or odd.
Yeah. Yeah, sorry, it's
okay.
It's a very simple question, but let me answer.
You continue with what you prepared.
Yeah. Yeah, it's funny because I actually thought about this, but I forgot what was my conclusion. But yeah, let's let me continue my story. So, what about, yeah, instead of writing I functions and j, like instead of writing I functions, I'll write it in the way I approached this story. So can we write an integral that analytically continuous corresponding, or maybe let's say some well-known objects, K theoretic I function for the quintic threefold. And here there are a few problems. So as I told you that this formula for disk partition function that gives analytic continuation of cohomological I functions is, I mean, it has very explicit physical meaning. So it's like Nekrasov formula. So like these Gaon functions are some determinants of one loop determinants, and this exponential is classical action, and this brain factor is some boundary action, whatever. So it has some direct meaning, and well, one doesn't have to invent this formula to give analytic continuation. It's somehow already there. The point is that there are formulas for analogous formula that produce partition functions in 3D theories, and like as is known in the folklore, that like cohomological computations correspond to two-dimensional theories and K-theoretical correspond to three-dimensional theories. So there is a way to write corresponding partition functions, but this partition, at least I failed to, and as far as I know, people who wrote this function also failed to try some kind of analytic continuation or comparison between Landau-Ginzburg and Calabi-Yau-Side. So what I did is just I was experimenting with different integrals, and at the end I arrived to some interesting formula, and today I want to present this formula, and together with Melissa we were trying to understand whether it gives something interesting or not. And so far we found something. So let me call this solid torus partition function. I'll put it in parentheses because it's not a partition function as I explained. It's some expression that I engineer specifically to be useful. So solid torus partition function. So for this reason, I call it Z twiddle D2 cross S1 of B. And yeah, what is interesting and maybe a problem related to this thing is that this B is same as in, so the brain is same as for dispatching function. So it's still a K-theory element.
Oh, so it's not some kind of elliptic object?
Yeah, that's the interesting part. So at the end, I used as an input some object that is not elliptic because I failed to make it elliptic because of, somehow it's not holomorphic symplectic. So yeah, maybe I'll write formula and explain.
Because sum of 1 plus 1 square 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 is not equal to 5 square. That's
Yes.
why I can't really be
Yeah,
elliptic.
exactly. Yeah, exactly. This is what happens. So, but what's interesting is that as you'll see in a couple moments, then some elliptic objects appear, and yeah, and my knowledge is not enough to understand what kind of object it is. So I can just write it, and so let me write the expression. Okay, so this is the expression for that I ended up writing after some trial and error. So if Q goes to 1, this expression, so maybe the integrand approach to the.
You use the functional equation for usual gamma function to put some of that in the denominator, and then you leave the sign from this functional equation there.
Yeah, exactly.
And then okay.
So I had to actually to preserve, in the what I wanted to do originally, I want to replace everything with some kind of elliptic functions, and then like this brand factor with some elliptic brand factors, but then I failed. And at the end, I had to preserve some of the, I had to preserve some trigonometric entities, like this sign and this brand factor, integrand of cohomological function. So this ZD2B. So this integrand is, one can write it as using Q gamma functions. Well, and again, there are several notations for them, but let me. So it's 1 over sine power 5 pi sigma. By sigma times gamma q of q1 minus sigma power 5, gamma q1 minus 5 sigma. Yeah, and then there is the usual exponential factor and the brand factor. Yeah, and as you mentioned exactly, so if q goes to 1, then gamma q goes to, so gamma q of in my notation q1 minus sigma goes to gamma of 1 minus sigma, and then there is a functional equation for reflection relation for gamma functions. And in the Q vault, it is something of the form in my notations. Theta function of Qx. But yeah, it turns out that I had to preserve some trigonometric part for this to make sense. Okay, I have to do Sorry, I think I have to. Oh no, it suddenly worked. Great. So let me study this expression a little bit in the remaining 10 minutes or so. So first of all, I want to so the thing I want to do with this expression is the same as I did in the cohomological case. So depending on sign of logarithm q, I want to either close the contour of integration to the right or to the left, getting either poles from actually let me let me use this color. So poles from here, and it will lead to the I function of xw, or poles from here, so from trigonometric part, and then it will lead to the I function, k-theoretic I function, of course, k-theoretic I function of y big W, or related with the k-theoretic I function of the quintic.
And the 24, 24-dimensional space, we can get counting these poles. Is that somehow, right?
Yes.
Okay.
So, yeah, this is exactly what happens. So I want to write. So I want to draw this poles on this diagram. So this is real part of sigma. This is imaginary part of sigma. Okay, and then first of all, the signs. The signs have poles where sigma is integer, and they cancel with zeros of this. Okay, yeah, maybe, yeah, most people know this, but I still want to write this expression. So this qx, q is a Q-Pogamer symbol, so this is just product from I, goes from 0 to infinity. The color changes. Y minus qx plus I. All right. So these guys have poles where sigma is positive. Sorry, have zeros when sigma is positive, integer. So this whole expression has poles at sigma negative integers of fourth order. Something happened, but let's not worry about this too much. All right. So this looks like fourth order poles, but they're actually third order poles. Third order poles corresponding to Calabi-Yau phase. And in Landau-Ginzburg phase, something interesting happens. Is that this Pogamer symbol has poles where 5 sigma is an integer, but we can also shift it in the imaginary direction. So this q1 minus 5 sigma q has poles if sigma is in positive integers over 5 plus I, 2 pi I rather. Because I mean, these elliptic functions, this q gamma function, they are also periodic in the imaginary direction. So we have not one-dimensional lattice of poles, but two-dimensional lattice of poles corresponding to this story. So 2 pi I over log q over 5 log q times z. So there is this two-dimensional lattice of poles, which is something that doesn't happen in. So yeah, something very similar happens in the in very old story of usual Mellon-Barnes integral for Gauss hypergeometric functions, like from old textbooks, maybe from many years ago. But yeah, in any case, the lattice of poles, so lattice of poles is two-dimensional in Landau-Ginzburg phase. And usually, as far as I understand, when people write like this kind of integrals in K-theory, people use not the Lie algebra variable, but rather, so variable not in C, but variable exponential of this one. So the variable that lives in C star, so in the actual Lie group associated to the gauge group of the JT quotient. But here I failed to do this exactly because 1 square plus 1 square, yeah, so 5 square is not equal to 1 square plus 1 square plus 1 square plus 1 square plus 1 square. So yeah, this is the price we have to pay, and exactly because of this two-dimensional lattice of poles, some elliptic object appears. So let me briefly describe it. So sorry. Okay. So first of all, geometric phase. So I won't spend too much time on this because it's what we expect more or less. So this Z twiddle of D2. Yeah, there are some convergence issues, but I don't think it's a good time to describe now. So it's K-theoretic I function times K-theoretic gamma class, which is, well, again, it's very similar to what was happening before. So there is no surprise here. And just this B plus. So this is some sheaf on some or other K-theory element of Z. Yeah, and in Landau-Ginzburg phase, something more interesting happens. So let me write the formula actually. So these poles that come from this expression are first order poles, so it's very easy to compute them. So if my notebook works, I'll write the formula. Okay, yeah. Shall I call this K? Sorry. Okay, actually, let me. All right. So poles at sigma is equal to K over 5 plus, and I want to split it. I want to split it as 2 pi I m bar over 5 log Q plus 2 pi I m over log Q, where m bar goes from 0 to 4. So I'm just taking residue modulo 5 of this second lattice. And these residues are exactly where these additional 20 solutions appear compared to the original story. Okay, let's hope it works at least somehow. So do I have like another 10 minutes?
Yeah, sure. Go ahead. I mean, it's the advantage of a Zoom seminar is that when people like learn what they already Yeah,
Yeah.
when people learned whatever they could learn, then they just sign off. So that's okay. Yeah.
Mhm. Yeah, sorry about it. Yeah, sorry, let me restart my notebook. It doesn't work properly. Oh yeah, I can erase finally. Great. Yeah, this is just Q inverse K. This is a residue. Then there is the usual factor, the exponential one. Okay, and then there is the fun part, which comes from the trigonometric part, because the elliptic part is actually the elliptic part. So this not elliptic part, but rather this Q gamma functions or Q-programmer symbols, they're invariant with respect to the shifts by 2 pi I m over log Q. What is not invariant is the trigonometric part. So we have sum over m in Z of this expression. So it's like exponential of minus log Q times 2 pi I m over log Q times f b of this expression over here. So this is, I mean, some big expression which you don't need to think about. I'll tell you what it is instead. So it's like a trigonometric expression. And then there are some imaginary arguments involved, so there is going to be some hyperbolic thing. And well, so this object over here is where you can see 24 solutions. So 24 solutions to difference equations. According to residues of K modulo 5 and this M bar. To K mod 5 and M bar. So, oh yeah, so what is zeta? Zeta is just fifth root of unity. So zeta is what happens here compared to the cohomological case. In the cohomological case, we have these gamma functions, which are like Q-programmer symbols are basically Q gamma functions. But there is no twisting by roots of unity. And this twisting of roots of unity is exactly what comes from this Kawasaki-Riemann-Roch formula, because our moduli space of quasi-maps is a stack, like, I mean, very simple stack, but still stack. And then if we use the Riemann-Roch formula, then we actually have to sum contributions from all the twisted sectors. And contributions from all the twisted sectors, they differ only by multiplications by some roots of unity. So this is where all these 24 solutions come from. Well, 5 times 5 is 25, but one of the solutions vanishes. So it's what I meant when I wrote 25 minus 1 is 24. Yeah, one can also see some beautiful, like this compares beautifully with the state space, but I don't have time, unfortunately, to describe this. And the interesting object is this one. So this is what I called an elliptic object. And actually, I managed to find some formula for this one. So formula. So this is the last thing I'm going to talk today. So formula for, let's call this star. First of all, let me try to speculate on like whether it's a section of some interesting line bundle or whatnot. Consider a function, periodic function, f of alpha is equal to f alpha plus 1. So an example would be this trigonometric expression. So e.g. f beta of alpha over sine 5th power by alpha. I mean, it's almost correct. There is some minus sign involved. Then this star over here is, so yeah, sorry, and introduce big E of log Q f of alpha is just a sum exponential. Sorry, let me actually look at my notes. Don't want to write something too wrong. Yeah, sum over m in Z, tau prime m log Q f of alpha plus tau prime m, where this tau prime is 2 pi I over log Q. So then, first of all, this star is E log Q over the following expression. E log Q of FB of alpha over sine 5th power by alpha evaluated at alpha is equal to some value. So alpha is equal to so k mod okay, let me write this k bar over 5 plus 2 pi I m bar over 5 log Q. So k bar is residue of k mod 5. Some value, doesn't matter. Then this expression had the following transformation properties. So first of all, it's still periodic. Second of all, if we shift alpha by t prime, then we get the same thing. Multiplied by prefactor. And then we can shift log Q as well. So if we shift log Q by 2 pi I over t prime, so these are elementary properties that are just immediately rid of the expression. And finally, the most interesting one is this one. So here there is some conjugation by this e2 pi I alpha. So in other words, you can think about an elliptic curve with coordinate alpha and elliptic curve with coordinate log q. And each of elliptic curves have two periods. So 1 tau prime here, and then 2 pi I and 2 pi over tau prime. So those are dual elliptic curves. And then this expression has the following transformation properties. So it's, if not 4, it transforms like exponential of minus log q alpha times section of Poincare line bundle. It's log q. Yeah, and finally, I write the expression for this sum explicitly in terms of some elliptic functions. So first of all, sorry.
So, are there some convergence issues with that sum? Are we supposed to imagine something about this
Right.
F alpha?
Right. So this is there are a lot of convergence issues, and actually the fact that I choose exactly these trigonometric factors are precisely to match convergence issues with the convergence issue of the cohomological integral. So there is the analogous rule for imaginary part of log q and weights of line bundles entering this brane B. So the convergence of this integral is exactly the same as convergence.
And so suppose we have this trigonometric function, right? We can take the trigonometric function and decompose it to the partial fractions, and then so there'll be an infinite sum, and then we get a double infinite sum, just Eisenstein series, right? That's the formula that's going to happen.
Yeah, I guess so. So I got it from a slightly different consideration, but yeah, it's basically so this f b of sigma over sine power 5 by sigma. So this is like Chern times Todd, or like Todd times Chern of b. So it is sum over ct exponential 2 pi it. So again, character decomposition of these brane factors. And then the formula is that this E log Q of it's additive. And then this is just 2 pi it sigma E log Q plus 2 pi it of sorry, it's, I'll write it in two lines. The first line and second line is E log Q of 1 over sine power 5 by sigma is LB of times theta of Q alpha exponential log Q minus pi I theta of Q alpha theta of exponential log Q minus pi I. And this is just some explicit linear differential operator in alpha, so of third order. So yeah, let me say finally a couple of words before I finish. So the formula that we have as Melissa of analytic continuation is some integral over still in the Lie algebra, not Lie group. So it's more like cohomological case, like cohomological integral rather than k-theoretic integral. But the integrate contains both Q objects and trigonometric objects. So the convergence of the integral is very similar to, at least in the imaginary direction, is the same as the convergence of the integral in the disposition function. The convergence in the real direction is another story, but yeah, maybe not today. And yeah, and finally, what happens is that even though we take trigonometric integrals in the expression, because of this double lattice of poles, at the end we get some elliptic expression in the Landau-Ginzburg phase. And we see all the 24 solutions to the Q difference equation. And at the same, yeah, so we see all of these guys, and then we see this elliptic object. But yeah, so far we don't know let's say the meaning behind this expression. So this is kind of where we are now. Yeah, and also we have slight generalization of these examples, but yeah, let me finish with this for today. So thank you for your attention and sorry for going over time.
No, that's fine. Let's all clap our hands in appreciation of Konstantin's effort. Questions?
So I had a question, kind of in the spirit of this like dual pair of elliptic curves. So like you could imagine a sort of modified version of this solid torus partition function, where in the integrand you replace these Q Pochhammer symbols by like Faddeev quantum dilogarithms that are kind of have this kind of dual elliptic curve built in. Do you think such a thing would have any meaning, or?
Yeah, actually, I need to think because I think so. Is it true that if you write some kind of integral with Faddeev dilogarithms, you'd rather have integral over Lie group rather than Lie algebra?
It would still be over the Lie algebra.
Oh, I see. Okay.
Yeah.
Yeah, thanks for the idea.
Because yeah, oftentimes the most sort of naive generalization of these kind of classical Mellon-Barnes integrals of gamma functions is you just replace all the gamma functions by Faddeev functions, and then whatever identity just continues to be true.
I see.
Okay.
Yeah, thank you. I haven't thought about this, but this might be yeah, because again there is no good reason for this integrand apart from the fact that it works, right? So so yeah, I'm actually like looking for maybe other possible expressions. So thank you.
More questions?
Do you know how this trigonometric piece of the solid torus partition function would look for more general GIC quotients?
Yeah, sure. So for one-dimensional models, it's actually like, if we consider degree R hypersurface in Pn, then like this becomes N, and this becomes R. So this is, for example, like, for degree. So, and the point is that you don't need Landau-Ginzburg-Calabi-Yau. You can have Landau-Ginzburg fun or Landau-Ginzburg general type. It's kind of discrepant things because here already you have non-balanced hypergeometric series. So in the usual Calabi-Yau Landau-Ginzburg in cohomological case, the hypergeometric series are balanced, and here it's not. So there is no big difference between like Fano, general type or Calabi-Yau, at least from the point of view of these formulas. And for more general types, yeah, I think I know how to write it, but I need to check it. But let's say have conjecture. We have conjectures with Melissa.
More questions? I had a question. So suppose you have one of the situations you in cohomology you had a quantum differential equation, and that was equation had whatever n solution when n was the dimension of your state space.
Yep.
Is the rule of thumb now that this sort of deformation that will have like n square solution roughly?
Yes. It's actually let me think a bit.
It depends on how stacked your modular space.
Yeah.
Because in the geometric case you have the same.
Yeah, thank you. Yeah, that's actually that's so you can see this from the state space. What as Melissa said, you have so you have to consider inertial, like inertial stack of so K theory of the inertial stack in the in the most orbifold phase of your theory.
Mm-hmm.
So somehow I have a feeling that
maybe you can you find the if you're on the direct side you think about some actual stack too, but that's making you find the remaining degrees of freedom there.
So yeah, that's an interesting question, and I don't have like a well thought answer, but so what seems to me after we discussed it with Melissa for a while, and it's kind of similar to what happens in the cohomological case in the discrepant transformation, when you let's say have degree d hypersurface, degree r hypersurface in Pn minus 1 where n and r are not equal. Then what happens is on one side you have kind of more geometric solutions than on the other, and on the physical language again, because I don't know this story from mathematical side too well, but on the physical side what happens is that let's say you have more solutions on Landau-Ginzburg side, say, then if you analytically continue the solutions that do not correspond to the geometric solutions on the geometric side, then you'll get what I call like massive vacua of the theory. So you have some conformal point, which is like nonlinear sigma model into like your Fano variety, let's say, or genotype variety, and then you have some massive vacua which are a priori not related with your what's it called? Yeah, with your variety. So yeah, this is kind of the answer. So on geometric side, I don't know how to.
Okay. So it's the comparison with this discrepant transformation. I think it's a good comparison. Yeah. Cool. And then this theta functions that you get. Is there a way to think of that as just some relative of the gamma class? Maybe you can just make up a story where that should be just a part of the gamma class.
So here's the thing. Apart from this elliptic guy, everything like the gamma class is literally the Q version of the original gamma class. So you replace gamma functions with Q gamma functions, everything works. This guy is like,
or maybe put it differently. I take back what I said. Can we look at your integral again?
It what, sorry?
Can we look at your integral again?
Yeah, sure. If I find it, sorry. Yeah,
here. So you see, you put the old exponential there as a function of Q, but in principle, you could put anything else that has the same kind of transformation.
Yeah, that's right.
So so maybe you just kind of, instead of, and since on on the geometric side, you only want to evaluate it at some very specific point. They have an incredible freedom as to what to put there as a function of q. So maybe it just tells you that redefine that function of q. That's all.
I see. Yeah, I think that's what I should try to do. That's because it seems very weird to me.
Of the capital Q, I mean.
So yeah, right.
Yeah.
Yeah, this seems like a very natural thing to do because yeah, another thing which kind of worries me in this expression for now is that like in geometric side we still get something which is at least doesn't look elliptic. In the sense that we still get k-theoretic I function with q-gamma functions, but we pair it with usual sheaves, not with like elliptic homology classes of sheaves. So this elliptic object appears like elliptic version of the Chern character or whatever appears in this integral on the Landau-Ginzburg side. So yeah, maybe adding some function of big Q to the integral might either change left side or right side. Yeah.
Okay. Well. All right. So maybe 2 hours is about. It's a good time to think about thanking Konstantin again. And
yeah,
in the old days, we would have continued this with the pizza conversation.
Oh yeah, I mean this all good days.
Yeah, but in the new days, I still encourage people, to chat and hopefully, learn more about what Konstantin and Melissa are doing and whatever. Contribute useful or useless advice.
Yeah, we will be very. We will be very.
With that, let's thank Konstantin again, and we'll meet again next week.
No, thank you, Konstantin.
Yeah, thank you.